Okay, we can get started. So for anyone new, this is Sami Kanderian from WikiModel, and they're going to be giving their talk on a web-based software application that enables teachers, students, scientists, and engineers to simulate, fit, and share mathematical models. I'll give it over to Sami, and thank you all for coming.
Great. Thank you all for being here. I'm excited to give this presentation. I will say that I'm not in academia. I left academia over 20 years ago as a student, but I have a passion for mathematical modeling, differential equations, and mentoring as well. My educational background is in biomedical engineering, which also sort of describes my career path. And to be honest with you, I didn't really enjoy my first differential equations class as an undergraduate. I took it in the math department, not the applied math department. I guess I took it in the pure math department, and I didn't really see the point of solving for analytical solutions of differential equations. But then, in my graduate project, I used differential equations, and then my career, I spent a long time in modeling insulin and glucose metabolism in type 1 diabetes, and that's sort of where my interest in differential equations took off. So, enough about me. I want to talk about my application. So I have developed this application. I actually started this way back in 2009, and I deployed it, I think, in 2017 or 18. But I never really presented it or showed it to anybody, and so I'm excited to share it with you now. Again, this is a web-based software application that allows teachers, students, and scientists and engineers to simulate, fit, and share mathematical models. And you can go to the website now, and it's wikimodel.com, and my email address is sami@wikimodel.com. If you have any questions, I'd love to hear from you. And then if you go to the website, you'll see some links where you can click on what it's about and how to use it on the top right. So again, what is WikiModel? It's a web-based software for simulating and fitting models. And the nice thing about it is there's no download or installation. It runs on the cloud via your web browser, and it's device and operating system agnostic. So it'll work on a PC, a Mac, an iPad, or any tablet, and a smartphone. And I've used it on all of them. I think it looks. I mainly use it on the PC, and it looks good on the tablet. I wouldn't recommend using it on a smartphone simply because the screen is too small. And the nice thing about this is it requires no programming, and and sometimes if you're new to if you're a new undergraduate and you have no experience programming, and you want to just learn math and differential equations, that can be a hindrance. I don't discourage programming. I think it gives you the maximum flexibility, but it can be a hindrance to new students. And the program handles any number of differential equations or closed form equations, and it also handles discrete inputs. So if you have an input to your system, you can input them as data, and then you can input them as impulses or steps or interpolated values. And I thought that was a good feature addition, because I remember when I was an undergrad, and when you simulate differential equations and you have sort of some things that happen at specific times, often the integrator, the Runge-Kutta integrator, won't necessarily stop at the timestamp that you want to put the input. So you have to kind of put that outside your description of the equations, and you have to write more code to do that. And this program will simulate the results and plot them on the screen. Another nice feature about it is if you have experimental data and you want to fit your model to the data, you can do that, and it'll estimate best fit parameters. You can also download simulated results, to a text file for further analysis if you would like. And you can also share your workspace. Your workspace is a model and data to the public, or you can keep it private to a specific group, let's say your classroom, for example. So, I want to show you a quick demo of it. So I wanted to pose this example, and this example is a well-known second order spring dashpot system where you have a mass and you kind of apply a displacement and you sort of let it go and see what happens. And the mass is attached to both a spring and a dashpot. And depending on these three parameters, you get a different response. And so I wanted to simulate that. So this is the standard form equation of it. It's a second order system. You to get differential equations on the left side, you rewrite the equation, and you can also make the following substitutions for some of the parameters. And the advantage of doing that is this eta parameter allows you to test underdamped, critically damped, or overdamped system, depending on whether it's greater than, less than, or equal to 1. And that gives you this equation. Now with with the simulator, you have to convert everything into a set of first order differential equations. And as you know, you can do that as follows. And the reason why I didn't fancy up make these two equations pretty is you can actually just copy and paste these equations directly into the WikiModel application. And so what I'll do now is show you the application. So can you guys still see my screen okay?
We see the login.
Yeah, great. That's what you're supposed to see. So when you first go, you can log in. And if you don't have an account, you can create one. It's free, so you don't need to pay anything to use it. Now I have an account already, so I'll log in with my account. You can also log in with your Gmail account, so you can bypass the whole registration process. The other modes of logging in aren't working at the moment, but the Google Gmail login does work. So, or you can just click on create a new account and do it that way. So I'll go ahead and log in with my credentials. And then what happens is it loads a bunch of, it loads the application. And what you see on the left is a bunch of workspaces or models that I've created. And I've created quite a few. And there are different examples that I've created. But let's go to the second order system that I have on my, that I showed on my PowerPoint slide. So I can search for it this way. So I could type in second order and hit enter. And there it is. So I click there and I click load selected model. And what you see is here are the two equations, right? So you have the rate of change in velocity is equal to this this equation on the right hand side. And then you have the rate of change of displacement is equal to velocity. And you also have to specify your initial conditions. So here, my initial velocity is 0, and my initial displacement is x initial or x ini. And I also have parameters, but so it's pulling this initial x value from this parameter table. So it's 3. And my eta value and omega value, it's pulling it from this parameter value. And so if I hit simulate, you'll see that here's my result, right? So here's my simulated result. We'll talk about the points in a little bit, but let's just focus on the green continuous curve. One thing we could do here is we could say, so here we've simulated it with an eta of 0.5. So I don't know if you remember, but if you have an eta value of less than 1, you have an underdamped system where you see these oscillations, and we can sort of exacerbate it with a smaller value of eta. So if I hit simulate, you'll see that the oscillations are exacerbated. Now, if you type in an eta of 1, that's a critically damped system. So if I type in 1 and I hit simulate model, it's critically damped, and so it doesn't have oscillations. And if you hit, something bigger than 1, let's say 1.5, and you hit simulate, it's 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 uh, it's overdamped. So now the question becomes, well, what if I had some data, experimental data points, and I really don't know what my eta, omega, and initial x positions are? Well, I could take an initial guess at them, right? I know it's underdamped because of the oscillation. So I could plug in I could plug in zero 0.8 and then hit simulate. But it's still not there. I could try again. Let's go back to 0.5. It's getting better, but what I can do here is once I have the data points in accessible to the model, and the way you can do that is by plugging them in here. So I have at time 0, I have this data point. At time 1, I have this displacement, so on. So I put in 10 data points. So now what you can do is you can hit fit model, and what it'll try to do is fit the model to the data and tell you what the output parameters are. And the output parameters are shown in the fit value column here. And you could see that the fit values are located here, and that's your answer. So and you can also download the results to your computer and analyze the data that way. There's some fit statistics that tell you how good the fit is. Now I'm going to go back to my my slides. So that's one example, and I've got, as you saw on the left-hand side, I had so many other examples, and I just wanted to highlight some of them. There's the predator-prey model, which was one of the student problems for the competition this year. And I modeled sort of the COVID outbreak in China based on this Nature publication. I used to work at IBM recently, where I modeled COVID cases in Hawaii, taking into consideration vaccinations and incoming infected travelers using an SEIR model. And then there's the Hodgkin-Huxley current clamp model and an electrocardiogram model. So I know there was some interest in showing the electrocardiogram model. I was talking to somebody earlier, and so I'm going to go ahead and, unless somebody has another preference, I'm going to go ahead and present that one and show sort of what that looks like. And so that second order system model was like 2 differential equations, and that was it. So this one has a lot more equations, and it's I didn't make up the equations. I got it from a publication, and I replicated it here. And so there's a number of equations, and some are differential equations, and some are closed form equations. The way the program knows differential equations is it looks for a d and a slash after the d. So in this model, there are 3 differential equations. There's dx, dy, and dz, dt. And here's the set of parameters in the model. You could see there's quite a few in this model. And then the last one, there was only 2. And here's the simulated results. So this looks like an EKG or an ECG electrocardiogram model, and that's the result. And so again, this is a tool that I built because it's a tool that I wish I had during my career when I was simulating the pharmacokinetics and pharmacodynamics of glucose and insulin. And so the frustration there was I enjoyed it. I enjoyed the coding, and it gave me the maximum flexibility. But anytime I wanted to change the model, you would have to rewrite the code and do a whole bunch of things. Now here, you could just change the model's equations on the fly and hit simulate in a matter of seconds. So I thought, I was in some other sessions earlier this morning where some professors were expressing, were saying things like, a lot of their students are new students and they don't understand how to program, and they can find it frustrating. So I hope that a tool like this would be useful for your students. And I really think I enjoyed making it. It was a labor of love, and I really hope that other people use it. And again, it's free for academia, so I hope you guys go ahead and use it. It does run on the cloud, so I do pay some fees, but it's fairly nominal, and I don't mind doing that. Is there a preference? I'm going to open it up now and see if there was a preference um, for me to present any of these other specific models. I will say that you know, you don't have to, you know, if you're interested in some of these models, you don't have to remember the links. You can search for the models by typing in the, you know, there some of the words in the name after the last backslash. And then tomorrow I'm giving a presentation on multi-compartment pharmacokinetic drug delivery at 5:30 in the main. So are there any questions, or does anybody want me to present a different model?
So in your electrocardiogram model, was there data entered on that one as well?
I replicated the model based on a publication. So the publication is here. Now, those guys kind of, I guess, identified some of their parameters from real data and showed that it matched up pretty well. But I just took their parameters that they used in their publication and I replicated it here. And that was the result I got. I did add some random noise to make it look realistic.
And I wouldn't mind seeing the predator-prey model, since I gave a talk on that earlier, to see if you can.
Okay,
Maybe
sure.
you can finish my talk in 2 seconds.
Okay. Were you the fella that tried to you showed some real data to see if it? Yeah,
right.
that was interesting. So I guess another nice thing about this is it'll give you a direct link. So if you share the link to someone, they could just click on it and it'll go there, and you can see that on the left hand side. So if I hit, not sure why it's let's see, because I'm not in presentation mode. Let's go back here. So now if I click here, boom, it brings it up, and there, you know, there's it. There's your two equations, and you've got the 4 parameters, right? And in this case, I have R and W. So R would be my prey or my rabbit, and W would be my wolf or predator. And you could see the simulated result here. And again, if you did put in some of that real world data that you gathered, you can you could plug it in here and fit the model to the data. And I get the sense that it would be tough because you showed that there was some drift and things like that. And obviously in these 2 equations, there's no drift that's implemented there. So, but you're willing to, you're welcome to give it a try, at least maybe give 1 cycle and see if you could fit sort of a chunk of the data instead of like
so
that.
But it would try to fit it, is what you're saying when you click.
Yes, it would.
Well,
yes, it would.
I'll get in there and try that.
Yeah, and you can also, as you saw in the second order system, you could, if you didn't know the initial conditions, you could also fit that by assigning a variable to it instead of plugging in a number, and then add the variable to your parameter list. You do have to give initial values, especially for differential equations, because it's doing a nonlinear least squares fitting routine, which requires an initial guess on all the parameters before you hit fit model. And you know, you could pick the variable you want to fit. So are you fitting the rabbit or the wolf profile? And you've got to plug in the data in here. You have to add a new data variable, and you can plug in the rows or columns. You can also upload the data as a text file if you want, and sometimes that's that if you don't enter it exactly right, or you have an extra comma or something, it won't work. So you could just type them in if you're more comfortable with that. I can make that upload process a little more robust by filtering out sort of errors and that sort of thing. But there's your predator. Let's change the, like, I don't know, what should we change? Should we change this to something like, I don't know, 50, let's say? So if I change, or no, that's the initial condition. Sorry, I meant to change one of these parameters. I don't know, is there any one of these parameters you want me to change?
Our model was very sensitive to the G and the H.
Okay, so should I half the G or something, or double it? Let me half it. So now if I hit simulate, there it is. See, there's your new output. So that changed the rabbit or the prey. Well, actually it changes both, right?
Yeah.
So, you know, it could change this one now. Let's
so the output for example, in the one we talked about, the scale of the populations were vastly different. Does it allow for different scales, or would one of those graphs be really small compared
No,
to
no,
the other?
it'll allow for different scales. You just have to plug in the parameters to match the scale that you're looking for. And they can be anything you want. So yeah, give it a whirl and let me know what you think. I mean, there's so many other examples. I have projectile motion. See if
I have a question. Can you get a phase portrait on these?
I'm sorry?
Can you get a phase diagram?
You can. So if I go to plot, right? So actually, I didn't show this. So here I had say in plot number 1, I want 2 of these profiles. I could say, well, let me add a new plot. I'm going to put that in plot number 2. In the x-axis, I'm going to plot, the rabbit, and on the y-axis, I'm going to plot the wolf. And there it is. There's your phase plot.
And can you get the equilibrium points on these? Can you change the parameters to get equilibrium?
Well, you would have to play with the parameters yourself until you get something you like. Again, if you had actual data, you could fit it to the data, but you could play around and until you get the numbers that you like.
Can I ask a question?
Sure.
Are you aware of anybody who's in an educational setting who's used this?
No, that's why I'm here. I want to tell you about it.
So this is really brand new to educators.
It's been around. Like I said, I think I put it up on the cloud. I put it up back in 2018 or 19. And I have some LinkedIn articles. If you go to my LinkedIn profile and search for my articles, I have several of these examples displayed there to kind of help people get started.
Okay. Looks very useful to students.
I hope so. I hope I don't die and nobody else uses it. That would be the worst.
No, it looks like a beautiful application. I have a question. So in physics experiments, very often one will do repeated measurements because it's the best way to obtain measurement uncertainties, to use standard errors instead of standard deviation. And I'm wondering, can this accommodate, like in the data section and for the fit, where you have the same X data, but you have different Y values, so that the uncertainties are more in the Y, but you have repeated measurements?
No, that's a great question, and I've given much thought to that. So, if this was my full-time job and I had the time to do it, even if it wasn't my full-time job, if I had time, that's something I would add. So you're saying you want to fit 2 data sets to 1 set of parameters. And that's a great question. And right now, it won't do that because each one might have different initial conditions and that's so on and so forth. So that's a great question. It won't do that today, but I can definitely build that in. It's not difficult to make that change.
Oh, great! Yeah, wonderful. It's something I've worked on with physics. In fact, I wrote a book with a colleague a few years ago on chi-square data analysis and model testing, where we utilize repeated measurements as a way of testing our models. So be happy to correspond with you about anything that might be helpful.
Sure, I'd love to. Yeah, I'd love to. I'll take your name down real quick. Harry Whitcock. And I think I'm sure Brian will have give me a list of emails so I can get in touch with you, but because I'm not sure of your contact information.
Sure, very good.
But I'm sure I could hunt you down on Google if I had to.
Yes.
Where do you teach?
Well, the book was written when I was at Harvard with my colleague. Actually worked at CERN originally, so he had a lot of experience, but it works well with as early as high school students. It's a very simplified approach. So it might work quite well here.
I hope so. That's the whole objective. Is I'm trying to get students interested by showing them applications and allowing them to simulate models and get results quickly. I was a judge on the competition this year, and there was a group of students, and they were very frank. They tried to get the predator-prey model working, and they used, I think, Mathematica, and they just didn't get results that made sense. But they, that's the results they had, and they presented on it, and they were very honest. And so I was like, oh man, if they could just, you know, they just plug in these two equations like you see here and hit simulate, you know, they could have gotten the results fairly quickly without any coding.
Yes.
Does this go until 4:55 or 5?
Hi, yeah, so I was actually just about to come on, so perfect timing. We are at the 55 mark, so if y'all would like to start transitioning to the next talk, there will be another talk in this room in about 5 minutes, so you're more than welcome to stay, but if not, please either go to the main room or room 2 to see the talks that are happening there. And thank you again for Sami. This presentation was amazing, so thank you so much for your time and your knowledge.
Thank you, everybody.
Thank you.